a scientist with the National Optical Astronomy Observatory, and he heads up the Office of Education and Public Outreach. And as you can imagine, having a bridge between science and sort of the non-science education is really, really crucial. But Steve is not just an interpreter, he is a great inventor. He managed to invent a telescope kit that went out to students, and those students were able to make their own original observations. But perhaps one of the most interesting things is, in fact, he's a secret home decor person. He has actually specialized in making the blackest black you can possibly imagine. In fact, you're even dressed for the occasion. So actually, Steve is going to be talking about his search for the blackest black.
Thank you very much. So if you were hoping that maybe I would talk about some black hole thing or some part of space that is away from stars and has no light and is really the blackest place in the universe, I hate to disappoint you. I'm going to talk about the things you see here in this art gallery, black paintings, black paint, things of that sort. And it all started in a very hot way, as I know it's hot in here, but people came into my office and said, we're designing a new infrared telescope to look at heat waves, and we think the telescope's not going to work very well because the coatings on the telescope don't seem to work very well. And we need to make a big change here or this project's going to be a complete flop, and we're not going to see anything that we want to see. So that was my challenge. And your challenge is to think about black not as a black paint, and I'm sure many of you have an artistic background, not thinking about the works of Mark Rothko or Rembrandt, for example, or Pierre Soulages, the French painter who specializes in black. Those are all beautiful things and worth looking at and talking about. But we have to think of black now as something that absorbs light. So we have sort of a continuum, and I brought a few props along. So we have to think of it, you can think of it as a paint, but you could also think of it as something that is on the continuum between white and gray and black. And what we had to do was go way beyond the continuum, much blacker than anything else that ever was seen. And we have one more challenge. I'm not sure this was part of the project exactly, but we took it as a challenge. I wonder if we can make something that's black all the way across the electromagnetic spectrum. Black in the visible light, so when you look at it with your eye, it looks black. Black in the ultraviolet, if you had ultraviolet eyes, like honeybees do, you could see it black. If you had infrared eyes, like a rattlesnake, you had the organs of a rattlesnake, it looked black, and so on and so on. Can you make something that's black all the way across the spectrum? That was the challenge. So we started thinking about this. How do we do that? Well, we have black paint, of course, and we know that the best black paints involve soot black. You actually get a candle and you hold up a piece of glass or a slide to it, and you collect some soot, and you have a very nice black, carbon black paint. That's been used by artists for thousands of years. There's also something called bone black, where you actually take bones of cattle or animals and you burn them in an environment with very little oxygen, and you actually get this very, very black material that is used in a lot of Chinese inks. In fact, just a little aside here, found out that in about 1892, the largest employer in Detroit, Michigan, was a company that collected buffalo bones, and this says something about what was happening in the Wild West. They collected buffalo bones and they burned them and they created this black material. And they were the largest company. I think they had almost 800 employees in Detroit in that time. Now they have 5 employees. They're still doing that. They're still making special inks for Rembrandt prints and so on. But now they have 5 employees. So it's the same company. Okay, well that's not going to do. So I thought, okay, I'll take these black things. What if I just made them a lot thicker and better? So I'll make them thicker and they'll absorb infrared light or ultraviolet light. Well, that was fine. I made very thick coatings and that seemed to be blacker. Okay, great. Okay, what if I put some chemicals into it that could absorb ultraviolet light or other infrared? For example, silicon carbide, which you use to sharpen saws, is a very good infrared absorber. That would be a great thing. Get some great silicon carbide, put it in the paint, and now it absorbs infrared light. But you got to be careful here because you got to get into a little different mindset here because You got to put yourself in the mind of an infrared photon, particle of light, or ultraviolet photon, or visible. And you got to get down on the nitty-gritty of these surfaces, because what's happening on these surfaces is happening on a microscopic level. So, for example, silicon carbide grit is nice and absorbing, but guess what one of the best absorbers of infrared light is? White particles. Titanium dioxide, what you put on your roof. It's the basis of a lot of white paints. That actually is a tremendously good infrared absorber. It's black in the infrared. So you can't just rely on what it looks like to the eye and think you're going to make it all work just as well. So why do we need this black paint on this telescope? Well, the telescope has the same problem you have when you're driving down the highway. Something's shining in your eyes. Maybe it's the sun. And what do you do when the sun is shining in your eyes? You put your hand up or you pull the visor down. Well, telescopes do the same thing. They pull their own visor down in front of them, and they try to block whatever's out there, especially space telescopes. And they also use black materials on the inside of the telescope, just like you have on the inside of your cameras or binoculars, in case light gets in there from the wrong direction. So if I'm looking at something straight ahead, and there's a bright light over here, and a bright light over here, and a bright light over here, and a bright light over here, that's all going to get bounced inside of my telescope, and it's going to screw up the image. It's going to decrease the contrast. It's going to make it a much softer image. And you're not going to get to see what you want. In fact, if you're looking for planets around other stars, you got this super bright star aimed into your telescope, and you want to look for this super faint thing nearby. You got to do lots. You got to put every trick you know on this to make it work. So anyway, I thought I had this problem solved. I the super thick black paint. I got the silicon carbide grid. I did some other tricks, and put all my tricks on it. There was only one little thing I forgot about. This material had to go into space. Space is a pretty rotten environment. It had to maybe be in low Earth orbit, where some telescopes are. There's a lot of atomic oxygen that erodes away materials. If it's up higher, there's a lot of charged particles from the sun. There's little static electricity that bounces back and forth on different parts of the telescope sometimes. So I wanted to test this material, so I got it out, and I put it in what we call a plasma etch chamber. It's basically like, if you took your microwave and put some metal in it and pushed the button and it went wild and you saw all the little lights light up, and then your microwave died and you had to buy a new one, that would be what this was. It was an etching chamber that was used to actually tear off material for semiconductors. So if you're making a chip, you would use this to etch off the material. So I put my little material in there, and I pushed the button that basically said, 3 years in orbit. What's going to happen after it's in orbit for 3 years? And guess what? Black became purple, became less purple, became gray, became white, became nothing. So in fact, it didn't even change color, and then it just disappeared. So all I was left with was the original metal material I put it on. So that approach clearly wasn't going to work. I needed to find something a little bit different, a little bit better that would work on this. So talked to the people in the metal shop, and they had found this really interesting anodized coating that was kind of a failure of anodized coating. So anodized is supposed to be nice hard aluminum coating. It had failed, and it created this very soft coating. If you looked at it under a microscope, it actually looked like a pine forest. It had big kind of things that looked like trees coming out of it. And the trees even had little branches coming out of them. And maybe the branches had little needles coming out of it. So I thought, wow, that is a really neat fractal surface. That would be really great at absorbing light. It would be kind of a maze. It would be, the light would go in, it'd never kind of get out. So that was my next trick I had to learn, is you want to try to make the light not come out. You want to create either a maze or holes in the surface or something that really will trap it. And maybe you want to make the surface very rough. So I brought along a rough surface here. And by the way, just a little quiz here. So I'm wearing black and kind of black pants, black shoes, and I have a black plate. And if you're really an aficionado of the search for black as black, you probably would have 15 or 20 different words for these different black. Maybe like the Inuits talking about snow and ice. There'd be all different variations. This is a glossy, specular, mirror-like glass surface. Then there's things that are diffuse black, rough black. There's things that are combination of specular and rough. There's things that, we have all kinds of nomenclature in science to try to describe these things. And a lot of them are based on experiments. So this is my shiny black surface. Here is my super rough surface. I'll pass this around. This is a rough, almost a spongy surface that's made of metal, and would be a good thing to put a black coating on. So this isn't black by itself, but if you put the black coating on, maybe it would be better. So I started learning some tricks. So the tricks were, how do I make it rough? How do I keep the light from being reflected? And really, the easiest way to think about this, you can think about it as two ways. You can think of it as taking a ball, you bounce it on the floor. If I bounce it on a nice smooth floor, the ball bounces real nicely. It comes right back up where you think it's going to be. Well, that's not what you want. You want to do the opposite of that. You want to find a whole bunch of children who leave all their toys on the floor and just make a huge mess of it. And then you want to bounce the ball, and you want the ball to go off in a different direction, because after all, if you throw a beam of light at something and it goes off in all directions, it may not be absorbed, but at least it's going off in other directions so you don't see it. So it looks fainter, it looks dimmer. So I started putting all my little tricks together, rough surfaces, holes in surfaces, chemicals that would absorb light. And then I wanted it to do it all wavelengths, so I had to create these kind of fractal surfaces that would be good for the infrared, have big holes to absorb the infrared, but little holes to, anyway. So you can imagine. So finally, I got my favorite surface together and put it in the spectrometer. I measured how it did, and it did fantastic in the ultraviolet. It did fantastic in the visible. It looked really black. In fact, I brought a piece of it here. This is actually a delicate surface. It actually looks a little bit like this other picture I'm going to pass around. So it's like little projections coming out of it. And I'll start this in the back of the room. This is a rough surface that's black, but you can see where somebody actually disregarded my instructions and actually put their finger on it. So it can stand the outer, it can stand space, it can stand storms from the sun, it can withstand atomic oxygen in the low Earth orbit, it can withstand years and years of everything. But the one thing it can't withstand is somebody putting their thumb on it, because it just crushes the surface. So you have to be very careful. So now, a number of years later, this is patented. We have a lot of secrets, trade secrets. We spawned sort of a whole industry of how to make things black for a variety of purposes, not just for space use, but for ground-based telescopes, for art purposes, for all kinds of purposes. And I just want to leave you with one final thought. So we needed this surface to go out to the edge of the universe, right? To see the new planets around other stars, to see the edge of the universe, to see the faintest objects. We really wanted to go back to our cosmic origins with this special surface on a space telescope. But I'd like to leave you with this thought. In a way, we're going back to our human origins as well, because we started in a dark environment. So we started in a place that was dark, and I think in a way when we start exploring and searching for the blackest black, in another sense, we're going back to a very primitive time for ourselves and searching for our own origins and our own emotional reactions to the dark. Thank you very much.